speaker for this session this afternoon is Juan Quiroz, who is joining us from Juan has been working this summer with Andrew and Ethan, and he'll tell us about their project together, modeling the effects of dark matter decays on halos and subhalos.
Hi everyone, thanks Gwen for that introduction. I'm very excited to talk to everyone about my project, but first we should talk a bit about dark matter in general and the motivation behind my project. The nature of dark matter is one of the most pressing questions in physics. It makes up a significant portion of the universe. However, it remains unknown, but we still have multiple candidates as to what dark matter could be. The most popular candidate is cold dark matter, which is stable, collisionless, and non-relativistic. Cold dark matter has been mostly successful in describing the universe in larger scales. Particularly, it has been consistent with the cosmic microwave background measured by WMAP and Planck satellite, as well as the large-scale galaxy clustering measured by SDSS. However, cold dark matter seems to have trouble matching some observations, particularly in smaller scales, like the Hubble tension that concerns the rate of expansion of the universe, the sigma 8 tension, which concerns the amplitude of matter clustering in quasi-linear scales. Also, cold dark matter simulations seem to predict a lot more satellites than the ones that are observed. Here I have a velocity distribution function. So it tells us the number of satellites, and in this direction, the mass is increasing. So the blue circles are cold dark matter, are results from cold dark matter models, and the triangles are results from observations. So we can see that for higher masses, they seem to agree somewhat well, but for very low masses, they disagree by a lot. It's almost like a factor of 10. Also, cold dark matter simulations predict a very high slope at the center of the density profile of the halo. So here I have a dark matter halo from M-body simulations, and at the center it has a really high slope, but this is inconsistent with what observations seem to indicate. So all these problems with cold dark matter matching observations seem to indicate that there might be a need for physics beyond the cold dark matter model. And that's where decaying dark matter comes in. We think that by altering some of the properties of cold dark matter, we could maintain its successes while fixing some of its issues. So decays are a natural part of the standard model. Almost every massive particle is known to decay. So it is not a strange idea to think that dark matter could decay too. Decaying dark matter models consist of a massive particle that decays into less massive daughter particles in timescales that are comparable to the age of the universe. A very simple decaying dark matter model would be a massive particle that decays into a less massive daughter particle and some radiation. The three parameters in this model would be the mass splitting and the lifetime of this decay. And it's important to note that this radiation would be in the dark sector, and this lifetime would be very large, so the decays would not negatively affect other astronomical observables. Decays produce shallower density profiles and fewer satellites. So in this image, I have results from an M-body simulation, and it compares cold dark matter and two different decaying dark matter models with different parameters for lifetime. And in this case, it's escape velocity, but it is related to the mass splitting. We can see that in both decaying dark matter models, they produce a fewer number of satellites than in the cold dark matter model, which these two things are some of the problems that cold dark matter has. Previous work has been done in modeling decays, but it has been with M-body simulations. In this particular project, we will be using Galacticus. Ellen talked a little bit about Galacticus this morning, but just as a refresher, Galacticus is a semi-analytic model for galaxy formation evolution. So it uses different approximations to solve numerous complex physics equations. Its main advantage is that it is computationally inexpensive compared to M-body simulations, which allows us to run larger samples and a better exploration of the parameter space. However, it comes with the disadvantage that it involves a greater degree of approximation, the extent to which has not yet been well assessed. However, comparisons between results from Galacticus and results from M-body simulations seem to agree fairly well, and this plot is an example of this. So this is a progenitor mass function. The red line are results from Galacticus, and the dotted green line are results from an M-body simulation, and we can see that they both agree fairly well. So the two main objectives for my project were to first create a model for the effects of the decay on an isolated halo, and then use that model to assess subhalo disruption. So we wanted to see if the decays would destroy subhalos that are orbiting around a more massive halo. By modeling the decays in a semi-analytic controlled way, we could bring insight into more complex simulations and bring to light key aspects of small-scale structure evolution in the presence of decays. So our decaying dark matter model, we will be modeling the very simple decaying dark matter model that I showed earlier. So just as a refresher, it's a massive particle decaying to a less massive daughter particle and some radiation. There are two important things that happen during this decay. The first one is that the daughter particle gains some velocity that is proportional to the mass splitting value. This velocity could then be translated into some heating inside of the halo. And the second thing is that this daughter particle has less mass than the parent particle. So there's also some mass loss occurring throughout time inside of the halo. And so we have to model both of those things. To model the effects of the decays, we model the heating introduced by the decays with a new heating class, and then we use a previous Galacticus class to handle the heating. Here are the effects of the heating from the decays on an isolated halo at 2 different times. So we're looking at the density as a function of the radius at 1 gigayear and 14 gigayears. The black line is the density profile of cold dark matter, and the different color lines are using our model with different values for lifetime and mass splitting. So we can see 3 very important things that happen when the decays are introduced. The first one is core formation. So we're seeing these flat lines. This means that there's a core that grows with time, and there's an explanation for why this occurs. The heating from the decays is independent from the radius, and it also increases with time. So it is able to surpass the binding energy for smaller radii. Galacticus doesn't really have a good way to handle this case, so this specific class assumes that the density in that region is uniform. However, we don't know how accurate that assumption is. The second thing is that the density profile is slightly reduced outside of the core. In this specific case, the difference between the cold dark matter and decaying dark matter model seems very slight. However, it's around 20%. It's just that the scale is located in this plot. And this third thing that we can see is that some of the halos are destroyed. These 2 halos that use larger mass splitting values do not appear in the 14 gigayear plot because they both go to 0. This happens since the heating from the decays exceeds the binding energy for all radii. We also modeled the effects of the mass loss independently. So to model the mass loss, we first updated the density profile by the mass loss factor, and then we added a new heating term that would be equivalent to the fraction of the binding energy that's being lost, and this would just simulate the reaction of the halo to the mass loss. Here are the effects of the mass loss on an isolated halo. So this is just the same plot as the previous one, but this one, instead of heating, it includes the mass loss. We found that the mass loss didn't have any significant change on the density profile. We had to use very large mass splitting values to see a visible change. And also, we can see that even though the density profile is slightly lowered, the shape is very similar to that of cold dark matter. Once we finished our model for isolated halos, we could add that model to a subhalo population calculation and see the effects that the decays have on the number of subhalos. So here we have a subhalo peak mass function, and it tells us the number of subhalos that are greater than a specific mass. And here we have the ratio of the cold dark matter and decaying dark matter model. So we found that the decaying dark matter decreases the number of satellites, especially the ones at lower masses. So at 10 to the 8, it's reduced by around 50%. Yeah, and now that we finished our model, our next steps are to calibrate the model more accurately to match M-body simulation results. So we made different approximations that we don't know how correct they are. So some of the things that we have to check are the uniform density assumption, and also we have to, for very large mass splitting values, the kick velocity is larger than the escape velocities. So those particles would just be lost instead of attributing to the heating. So we would also have to check that in our model. And once we do that, we can then use observations of dwarf galaxy populations to constrain the parameters of our model. And yeah, that's it.
All right, very nice. Questions for Juan?
So in one of your graphs about subhalos, you also had like the regions that were marked, like not only the line, but also some highlighted regions.
Oh.
So what are the highlighted regions specifying here?
So these are discrete numbers, but they also have some uncertainty to them. So that's just the Poisson error, and that's mostly because in this region we can see that the decaying dark matter surpasses the cold dark matter. However, that just might be due to the error, because we see that these areas overlap, and not because the decaying dark matter produces less of halos. However, in this region, the two areas don't overlap, so we can see that that's probably due to our model and not just some error.
Yeah, I might have just missed this, but when dark matter is like decays, is there a minimum like decaying mass that dark matter can turn into?
Like the mass splitting value, like the minimum mass that this can have. Not really. Like, I guess we have some observational. We could have some observational constraints on the mass splitting value. However, in this model, we haven't really implemented any constraints on it. The thing that I said was that if the mass splitting value is too high, then this velocity will also increase and would be the particles would just escape from the halo instead of adding to the heat.
Other questions for Juan?
Yeah, thanks. So for the density profile, why, just because the dark matter is decaying, it has such a sharp cutoff at the halo center?
So the assumption of this model is that we think that the binding energy is equal to the heating from the decays at this exact cutoff where the straight line ends. So this model just assumes that this density in the region inside of it is uniform. However, we don't know how accurate that assumption is.
All right, let's thank Juan again. All right, let's have another round of applause for our 6 excellent speakers.